Okay, hi everyone. So today we are going to talk about chapter 1, and this is in chapter 1, section 2. So what we are going to talk about, we are going to talk about electric potential energy and electric potential. So C1S2, electric potential energy and electric potential. Okay, so by this title itself, I hope you all notice that electric potential and electric potential energy, they are two different things. Okay, or else I won't write it two times, right? Okay, so electric potential is definitely not electric potential energy, but forgetting the word energy. Okay, it's a totally different thing. So I hope all of you can take note of it. Electric potential energy is a kind of potential energy. When we talk about electric potential, we are talking about the electric potential energy per unit charge. So it's a bit different, the meaning here. So they are two different things, not the same thing. Okay, so I'm going to start my session today by talking about electric potential energy first, because I think electric potential energy makes more sense to you right now because you have learned about gravitational potential energy, you have learned about elastic potential energy. So starting from potential energy might makes more sense compared to starting with electric potential. Okay, so electric potential energy, the symbol is U, just like any other potential energy. And the unit for electric potential energy, it's because it's an energy, so it will be joule. Okay, stop. What happened? It be in joule. Okay, so this is the start of my session for today. Okay, so because it's an energy, we know that electric potential energy is definitely a scalar quantity and it has no direction because it's an energy. Okay, so this is unlike what we learned in section 1. Section 1, everything that we learn, electric field, electric force, those things are vector quantity. It has magnitude, it has direction. But right now we talk about potential energy is an energy, so it's a scalar quantity, it has no direction. Okay, but you can have positive and you can have negative value for potential energy, just that the positive and negative here doesn't carry any directional meaning. It just means that it's greater than 0 or it's less than 0. Okay, so electric potential energy, if you want to really focus on the definition is it's the work done or the work required to bring a charge from infinity. Okay, we are going to start this charge from infinity to a specific point in the electric field. Okay, so the charge was initially somewhere very, very far away. That's why I call it infinity. Somewhere infinitely far away from the space that has electric field. Let's say this particular space it has electric field here. The charge is initially outside of this electric field, somewhere infinitely far away, far, far away. Well, what you're going to do is you're going to bring that charge from somewhere far away and bring it into this electric field region over here. So when you bring it in, it requires some work to be done. So if you manage to calculate the work that needs to be done to bring that charge over into this electric field to that particular position, then that work done itself will be the electric potential energy stored in the system right now. Okay, it's a bit complicated to explain based on this definition because we know work done, but work done is something very abstract to understand. Let's probably change it to something more physical, something that is easier to imagine for now. Okay, so now I'll try to talk about how can we imagine about electric potential energy. Okay, so because the definition is too difficult to understand, let's maybe try to imagine electric potential energy in the more concrete way, something that you can easily imagine. Okay, but to imagine electric potential energy, I'm going to visualize it with something that you have learned from last semester, But before we start, right, I'm going to talk about two different scenarios that will be important for our discussion here. Okay, so I'm going to split it into two. Okay, there will be two scenarios that I'm discussing over here. So the first scenario that I'm going to discuss is a pair of like charges. Okay, we're going to talk about a pair of like charges. So like charges means they are charges that what do you call? Charges that have the same polarity. So it can be a positive charge. Okay, they have the same polarity being positive. Or another scenario that we are going to study later is a pair of opposite charges. Okay, a pair of opposite charges means they have opposite polarity. So if one of them is a positive charge, the other one will be a negative charge. Opposite charges. Okay, so what do we know? We know that if it's a pair of like charges that are interacting with each other, we know the interaction between them will be a repulsion because they have the same polarity, they repel, right? So we know that the normal reaction that will happen to a pair of like charges is they will repel each other. They repel. Okay, but if you talk about a pair of opposite charges, a different kind of interaction will happen. You know that opposite charges, because they have opposite polarity, they are supposed to attract to each other. So you suspect that they will attract right now because they are opposite in charges. Okay, right now what I'm doing are all very logical thinking. It's what you learn from electric force and electric field. You know that like charges repel, opposite charges attract. Okay, but one I want you to visualize right now is, let's say this universe here has only a pair of like charges. Let's say this whole wide universe, there's only a pair of like charges, positive and positive. Okay, so because there's no other mass in the universe, so you don't need to worry about gravity over here. There's only these two charges. There's no gravity that needs to be taught over here. So let's say if we have only a pair of like charges and we let go of our hand, okay, let's ignore there's no me, okay, there's no hand either. I just let the two charges be there. So what will happen to that pair of like charges is, because they are positive or negative, they have like charges, they repel. So when they repel, they try to push each other away. So if you try to imagine a situation, how far away will they keep pushing each other towards? Okay, so if I push away like 100 meters already, is it enough? Will I still continue to push each other away until I reach like a few thousand kilometers? When I reach a few thousand kilometers, is it still enough? Will they still keep pushing each other away? Well, we know that the force in between these pair of charges, they are controlled by the Coulomb's law. Okay, F is equals to kqq over r squared. So know that the force will forever be there for a pair of charges, because as the r increase, the force decrease. But the force never decrease to zero actually. If you want the force in between these two charges to equal zero, what you need to do is you have to increase the distance until infinity. Means by the distance between these like charges has to be infinitely far, only you will see that the repulsion force between them goes down to zero, and now they will no longer push each other away anymore. So they will only stop pushing each other away when they're infinitely far away from each other. So that means if you let the two charges at their own, what happens is they will try to get as far away to each other as possible, as infinitely far as possible. When they get far away, they only want to go further. So naturally, at the end of story, these two charges should be infinitely far away from each other. Okay, so based on that idea, I'm going to say naturally they want to get as far away from each other as possible. Okay, but if you talk about a pair of opposite charges, the opposite will happen, because you know that they want to attract each other, they want to move towards each other. So what happens is, if you let them go, you let them be at their own, what will they do is they'll try to get as close to each other as possible. So what is the closest distance between them? Well, it's equals 0, right? Distance between them will be equals 0. They basically just stick together. Okay, so you know that if we are talking about a pair of opposite charges, what they do is they naturally they want to get as close to each other as possible. Okay, so that is what you should expect for a pair of like charges and a pair of opposite charges. If it's like charges, they want to be as far away as possible. If it's opposite charges, they will try to be as near to each other, as close to each other as possible. Okay, so knowing this fact right now, what I'm going to do is I'm going to ask you to try to imagine this scenario over here. The scenario that I'm going to ask you to imagine is, let's say we have a pair of positive charge. So this is a positive. Okay, let me redraw it a bit. Okay, let's say I have a pair of positive charge. So this is a positive Q1. This is a positive Q2. Okay, and the distance between this pair of charge over here, the distance between them, it's R12 right now. Okay, so right now, if we choose to bring this pair of charges too close to a distance of R12, means that we don't want to let it just get as far away as possible, we bring them to a certain distance R in between them. That means by you are actually forcefully bring them to a certain distance together. Okay, they want to be as far away as possible, but you are forcing them to not be too far. You want them to be just far until the distance between them is R. So you are forcing it to happen. Okay, so if you think about it, if they naturally want to be infinitely far, it is as if it was a spring that is originally, when you don't compress it, when you don't stretch it, they are infinitely long. That spring is infinitely long. But what happens is, if you bring the two charges to a distance R in between them, it's as if you have to force the two charges at the two ends of the spring to move towards this distance R over here. Okay, you have to bring them to this distance R. Well, that means you are like compressing the infinitely far, infinitely long spring to a distance of R. Okay, because they want to be infinitely far away from each other. That means that when they are at equilibrium state, or when they are at rest, or when they are in relaxed position, they are infinitely far. But you're forcing them to be close together at the distance of R. So it's as if you're forcing them together. It's like you're compressing that infinitely long spring to a length of R. Okay, so with this explanation, I'm going to write something here. I'm going to say what we are discussing here. If you place a pair of like charges at the distance of R, you can think of it as being equivalent to, you take a spring, which is initially infinitely far, infinitely long, okay, so this is my spring. Right now it has a length of infinity, but infinity, let me write it more clearly. This is infinity. But right now, what I'm going to do is I'm going to compress this spring. Okay, it's equivalent to this infinitely long spring being compressed. What am I doing with my spelling today? Okay, so right now you compress it to exactly the length, which is R. So right now the spring is no longer that long. It's being very compressed, and it is compressed to a distance which is R. Okay, so you are forcing something to happen. You are forcing the two charges which want to be as far away as possible. You are forcing them to a distance of R. So it's as if you are compressing a infinitely long spring over here. Okay, on the other hand, if you look onto the case which involves a pair of opposite charges, Now, if you think about a situation, if you want to have a classic situation in which you have a pair of opposite charges, right now, let's say this is QA. Let's say we have QB on the other side. And the distance between them is RAB, let's say. Okay, if you want to make this setting happen, where QA and QB are at a distance of RAB between them, this is as if, okay, this is on the opposite side of the story. Just now the spring was infinitely long, but right now we're talking about a pair of opposite charges here. So a pair of opposite charges, they want to be as close together to each other, right? So it means like if you let them be, they'll stick together. But right now you're forcing them to be at a distance of r in between them. So it is as if you're taking a pair of charges which is sticking to each other, you're forcefully pulling them away. So when you're forcefully pulling them away, it's as if you take a spring which was infinitely short initially, like the length of 0, they're sticking together. So it's as if the initial length of the spring is 0, but you're going to pull it until the length of the spring becomes r. So it is an action as if we are stretching a spring over here. So this setup here is as if you're taking an infinitely short spring. So we can call it a 0 length spring over here. Okay, so I'm going to write so it should be purple, sorry. Okay, so this is a spring, infinitely short spring in which the length is equal to 0. But what you're going to do to this spring is you're going to stretch it. Okay, you're going to stretch this spring until it reaches a length of r, right? Okay, so because why do I try to relate it to a spring? Okay, try to relate it to a spring because it's some sort of like a forceful kind of action. You're trying to bring them to a certain distance, either by compressing, like very hard to bring that two positive charges together, or if it's a pair of opposite charges, it's as if you're trying to separate them to a distance. So because it's kind of like a forceful action, I relate it to a spring. And the real reason why I want to relate it to a spring is because when we compress a spring, or when we stretch a spring, we know from last semester when we talk about work, energy, and power, a compression of a spring or a stretching of a spring will cause elastic potential energy to be stored in the spring, right? Okay, energy is being stored in the spring because we stretch a spring or we compress a spring. So now, if I think of this a pair of charges kind of situation as a spring being stretched or a spring being compressed, we will naturally think that it should be logical that there is some kind of potential energy stored in between them. Okay, because if we can make sense that it is as if we are compressing a spring or stretching a spring, we know that the action of compressing or stretching a spring will store elastic potential energy. So this kind of situation is similar to stretching or compressing a spring. They should also store potential energy. So what you guess here is true. They will indeed store some kind of potential energy. And to be perfectly clear, the kind of potential energy that they will store over here is the title of today's section. They will store, okay, I should be a bit more clearer, a pair of charges you can say store, or you can say possess, or you can say share. It's up to you. I'll just say store, okay? A pair of charges store electric potential energy, which and later I'll be short forming it to be called as EPE. Okay, so that's the idea that I'm trying to convey over here. Electric potential energy is hard to imagine. Why do we have electric potential energy? But if we try to relate it to a spring right now, you can see that any pair of charges in between them will store some kind of potential energy, because the whole action of bringing a charge to a certain distance, it somehow looks like stretching a spring or compressing a spring, depending on whether I like charges or opposite charges. So we know spring, if you stretch or compress it, store elastic potential energy. Bringing the charge to be at a distance away from each other, that action itself will also store some kind of potential energy. And as we know, the kind of potential energy being stored in between them is called the elastic potential. It's called electric potential energy. So usually, to make it clear that there's some kind of energy being stored in between a pair of charges, I'll usually sketch a spring in between the two charges. Okay, a spring, I will draw a spring in between the two charges. In this case, this spring here is a compressed spring, and because it's a compressed spring, it will store some kind of potential energy. And the potential energy that's going to be stored is called U12, which is the potential energy in between Q1 and Q2. So for this one, there will be a spring between them, but this one is not a compressed spring. This is a stretched string. Let's stretch spring right now. So the potential energy being stored in this spring here is called UAB. Okay, the spring is just the figment of our imagination only. There's no such thing as a spring in between, but you can think of the interaction between them is as if you are manipulating a spring over here. So that's why you possess electric potential energy. Okay, so that's the first part of my explanation here, to try to help you make sense of the potential energy that we have over here. Now I'm going to use, now you have a rough idea of what is electric potential energy, right? What I'm going to do is I'm going to explain or recall some ideas from last semester. Okay, I'm going to recall the idea of work done from last semester, so that later we can spend some time to really dive into the definition that we have over here. Okay, over here we have the definition of electric potential energy, and it requires it to be explained in terms of work. But work is maybe not something that you all are familiar with, so let's do a little bit of refreshers of what is work done first. Then maybe we can use that what we have refreshed about work done to study this definition in greater detail. Okay, so this is a bit of a refreshers from last semester, so I hope you can pay attention. So right now I'm going to discuss about, let me write it down. I'm going to discuss about the work done by two things. I'm going to discuss the work done by electric force. I'm going to also discuss the work done by external force. So these are the two types of work done that I'm going to analyze based on the right now lah. Okay, I'm going to analyze these two types of work done. Okay, so to do this, I'm going to recall something from last semester. So what I'm going to do is I'm going to split it in half, where the left half is something like a recall, then the right half is what we are going to learn in today's session. Okay, so we're going to drag something from the last semester and bring it to this semester. Okay, so let me slightly set up the situation a little bit. Okay, just nice. Okay, so on the left hand side here, I'm going to compare. I'm going to compare between two situations over here. Okay, the situation on the left is what we learned from last semester. The situation on the right is what we are going to learn right now. Okay, so last semester, okay, to be more specific, in chapter 4, okay, in 2024 is chapter 4. Okay, I don't know in the future years what chapter will it be. Chapter 4, which is on work, energy, and power. Work, energy, and power. Okay, we learned about a scenario which is very simple, which I'm going to discuss with you right now. So this scenario involves a ball moves upward with constant velocity. Okay, it's a very simple example. We have seen this before. Okay, we have discussed this kind of question. Almost every one of us has discussed this in chapter 4 before. So what it involves is, let's say this is your ground. Okay, and now we have initial, we have final. Okay, let's write it down. Initial is here. On the left hand side, final is on the right hand side. Okay, so the ball moves upwards, right? Means by initially it was at the lower position. So I'll label this as my initial position of the ball. Then after that, it will undergo some kind of displacement going upwards. So I'm going to label it by this S. And in the future, at the end of the journey, the ball will reach this final position. Okay, initially the ball was at a lower height. So initially, if you want to measure the height here will be called as H initial. Okay, the initial height. But as you move to a higher place, your height has changed, right? So now you have entered a new height, which is what we call as the final height. Okay, so this is a very simple scenario that we are going to study right now. And because we want to study the work done, it's best that we understand what are the forces involved over here when the ball moves upward from this initial position to this final position. Okay, the ball is moving upward with constant velocity. So we know that constant velocity means that our we have to analyze this situation using Newton's first law. So you have to do sum of Fy is equals to 0. Okay, because constant velocity, your force must be in equilibrium. So let's say if you draw the free body diagram of the ball when it is at this position, what you have is you have your weight pointing downwards because this ball has mass. Okay, but because you want to move this ball upwards with constant velocity, you need an upward force to balance this weight that we have down here. The upward force that we use to balance this weight up down here will be the external force. Okay, in this case, the force exerted by a robot or by my hand or by anything to push the ball upwards. But because the force pushing upwards and the weight pointing downwards are balanced, they have same magnitude but opposite direction, the sum of force will be equal to 0. Therefore, the kind of motion experienced by this ball is a constant velocity motion. Okay, so if I want to analyze the free body diagram in terms of Newton's first law, what I can say is that the sum of Fy equals 0. And because sum of Fy is equal to 0, we know that the force external minus the weight, both of these will be balanced, will be equal to 0. So you know that the force external over here, which is my hand or the robot or anything, will be equals to the weight, and therefore equals to mg. So this is what we know in terms of analyzing a free body diagram using Newton's first law. But at the same time, we know that because the object moved from a lower height to a greater height over here, the change of height here will change the gravitational potential energy of the object. Okay, so it's best that we can determine the gravitational potential energy initial and the gravitational potential energy final. We know that the initial gravitational potential energy is U initial is equals to mgh initial, whereas the final gravitational potential energy is called U final. It's equals to mgh final. Very straightforward, what we learned from last semester. Okay, so this is a situation being analyzed thoroughly. Now, let's say I would like you to determine two things for me. The first thing I'd like you to determine for me is the work done by gravity. Okay, so if you want to analyze the work done by gravity, because work done by gravity is this weight over here, and weight is a constant force, we can just find the work done using a simple W is equals to Fs cos theta, right? But the force over here is weight, so we immediately change it to mg. So this will be mg s cos theta. Okay, mg represent the weight, the force, which is Fs cos theta, but force is the weight, then therefore this mg, s is the displacement, theta will be the angle between the force and the displacement, and this will be the angle between the weight, w with an arrow, and displacement with an arrow. Okay, so we further expand this equation over here. mg, there's nothing to expand. But we know that this displacement here, S, is actually can be determined by taking the H final minus the H initial over here. So we'll write this displacement as H final minus H initial. And afterwards, for cos theta, which is the angle between weight and the displacement, we know that weight is pointing downwards, therefore displacement is pointing upwards, therefore they're in opposite direction. The angle between them will be 180 degrees. Because it's 180 degree, you know that cos 180 degree will be -1. So what I will do is I'll bring this -1 to the front. Then right now your weight will be equal to negative with an mg h final minus mg h initial. So what I do is I expand the mg into the hf and hi, but I leave the -1. I don't bring it into the bracket, I leave it outside the bracket. So this is what I get over here. Why do I want to arrange it like this? Because as you can notice, mgh final is the u final, the potential energy final. mgh initial is the potential energy initial. So right now we can change our equation to be expressed in terms of energy. So this is uf, whereas this is ui. So if you write like this, you definitely see that final minus initial energy. That means by what we have in the bracket here is actually the change of potential energy. Okay, so work done by gravity, which I'm going to write by Wg, work done by gravity is actually negative change of the gravitational potential energy. So this is the first important thing that I think is worth mentioning when we are finding the work done by gravity. We find that if we are talking about gravity, then we are talking about gravitational potential energy, right? Then we find that the work done by the gravitational force or by the gravitational field or by the weight over here, the work done by the gravity over here is equals to the negative of the change of gravitational potential energy. So the gravitational potential energy is actually related to the work done by the force that causes this energy, which is the gravity. Okay, the work done and the energy can somehow be related through this equation over here. Okay, the second kind of work done that I want you to determine right now is the work done by the external force, which is the other force that we have over here. Okay, work done by external force. So if you are finding the work done by external force this time, I believe most of you can probably notice that it's similar actually. It's still Fs cos theta, but this one is not weight, so we don't change it to mg immediately. We write external force times S times cos theta. But this time theta is a little bit different. This theta is the angle between the F external and also the displacement. Okay, F external, we know from what we analyzed in Newton's first law, F external is just equals to mg. So this can be replaced with mg. The displacement is again h final minus h initial, nothing to worry about it. But right now, if you look at the angle between F external and S, F external is pointing upwards, the external force is pushing it upwards, right? At the same time, the displacement is also upward. So we know that the angle between them is 0 because they are in the same direction. So cos 0 degree we know will be equals to +1. So right now there's no more negative sign. If you expand your equation will just be equals to mgh final minus mgh initial. And this, I believe, all you can see is just uf minus ui. And therefore, we can come to a conclusion. If you're finding work done by external, it is similar but not the same. What you get here is you get delta u instead of negative delta u. So what I hope you can notice right at this point is that if we find for constant velocity, for the work done by gravity, you get negative delta u, but because F external is same magnitude and opposite direction, just to balance the weight, therefore the work done by it will also be the same value but opposite sign. Okay, same value by opposite sign. So you see this one is negative sign, but work done by external is a positive sign. Okay, so if we find the final gravitational potential energy, minus it with the initial potential energy, that value here will be delta u, right? So that means that is the exact amount of work that needs to be done by this force external in order to make in order to cause this change of potential energy. Okay, so because you see that these two are similar equation, just that one has negative sign, one without negative sign, you can actually come to a conclusion that they both share the same value, just that they have different sign. So we can say that work done by gravity is actually equals to work done by external, not exactly equal, but they have different signs. So there's a negative in front. So this is the relationship between the work done by gravity and the work done by external force. Okay, the whole explanation here is something that you have learned before from your last semester, but I think it will be helpful because we are going to bring this conclusion that we have determined here, the three things over here, we are going to bring it to what we are going to learn in this semester. So this semester, things change a bit. We no longer talk about balls on Earth anymore. So in this semester, okay, in particular in chapter 1, section 2, what happened is we now have a pair of charges instead. Okay, we don't want to talk about ball and floor anymore. We talk about a pair of charges, but we still want them to get further away. In this case, a ball is getting further away from the Earth. In this new case, a pair of charges here, they are just moving away from each other. But we don't want them to just move away from each other like this. We want to move away from each other with constant velocity. Okay. Okay, we still want the motion of the charge to be same speed, same direction. We don't want it to make any bend. We don't want it to speed up. We don't want it to slow down. Okay, so again, we're going to sketch a situation just so we are all clear with the situation that we have right now. So it involves an initial situation and a final situation. So initially, we say the charge is close, right? Only then after that, it gets to move away. They get further and further apart. So initially, I'm going to look at a pair of opposite charges. Why is it so? I'm going to look at a pair of positive charges because a pair of not positive charges, a pair of opposite charges. Okay, so I have Q1, which is positive, and I'm going to have another charge, which is a negative charge, Q2. And the distance between them right now is called R12. Okay, but because these two charges are moving away from each other with constant speed, let's say if we fix the position of this positive charge Q1, well, we can see that if they are moving apart from each other, Q2 will have to be at somewhere even further away. So this is the position of Q2. Okay, so now the distance between Q1 and Q2 has already changed from R12 to R12. We need to differentiate between them. So right, this is R12 initial, this is R12 final. Okay, so why do I say this scenario is very similar to the scenario on the left? Because we know that the ball get extracted to the ground. In this case, the negative charge here also get attracted towards the positive charge. Of course, the Earth will also get attracted, not Earth, the charge number 1 will also get attracted to Q2, but we are not focusing on Q1. We are focusing on Q2. So we just need to look at the forces that are acting on Q2. Okay, again, I would like to say they are moving away from each other, so you should expect that Q2 is moving in this direction. So this will be our displacement over here. Okay, so Q2 itself will represent, you experience an attractive force because down there there's Q1, Q1 is positive. So you experience an electric force pointing downward. But at the same time, we know that because we want to move with constant velocity or constant speed, why do I write speed? If we wanted to move away with constant velocity, what we need is we need Newton's first law. So Newton's first law says that force need to be in equilibrium, right? So if you want our force to be in equilibrium, we know that the sum of force must be equals to 0, just like the usual, because we want to be equilibrium. Okay, So sum of Fy over here, instead of having F elect only, we need another force in an upward direction. Why do we need another force in an upward direction? So that the sum of force will be equal to 0, up and down balance, only we can move with constant velocity. So what's the another force that is pushing it in the opposite direction of the electric force? Well, I guess all of you can know it. It's the external force, some kind of hand or some kind of tool to bring the charge further apart. So right now, this charge here will face a similar fate like this ball over here. This ball faces two forces, but these two forces are in equilibrium, the external force and the weight. On the other hand, in this situation, Q2 also experiences equilibrium, where you have external force pointing upwards and electric force pointing downwards to form a balance. And because sum of Fy is equal to 0, you can say that this is equivalent to taking F external, which is pointing upwards, minus F electric, which is pointing downwards. And the result, the difference between them should be equal to 0. That means by the external force and the electric force should be having the same magnitude, just opposite direction, so that they can balance each other out. So from this statement itself, we can know that the F external, the external force, is actually just equals to the electric force. In terms of magnitude, the external force and the electric force have the same magnitude, but they're in opposite direction. That allows the charge to move with a constant velocity. Okay, so we know that because we talk about a pair of charges, we have spring in between them in my story. So we can draw a spring in between them. So there's spring in between them. So this one will store an amount of energy called U initial, whereas this one will also store another amount of energy because the spring has changed its length. So the amount of energy stored will have changed as well. So this will be U final. Okay, it's a similar scenario, but just now I'm going to relate it to the spring that we discussed just now and say that in between every pair of charges, there's a spring. So if the charge moves apart from each other, the process itself is changing the amount of compression or the amount of stretch that happens to the spring, and therefore the potential energy stored in the spring or the electric potential energy stored in between these two charges will change. It will change because the spring will length change, just like how you change the stretching or you change the compression of the spring. The elastic potential energy changes, right? So here the electric potential energy will change from Ui to Uf. Okay, again I'm going to find two work done. I guess you might have known what two work done I'm going to find. The first work done that I'm going to find is the work done that has replaced gravity right here. It's the work done by the electric force. Okay, so work done by electric force over here, electric force pointing downwards, is actually very similar to the function of this weight over here, pointing downwards. So if we obtain some conclusion from work done by gravity, we know that it's very similar to the work done by electric force, because the electric force over here is in a very similar role to the weight over here. So what we have derived over here can actually be shifted to be the work done by electric force, because they are very similar in terms of their behavior. So we can therefore come up with a conclusion right away without any derivation, because we say that if it's true for gravity, it should be true for electric cases as well. So you straight away and say that this is work elect, okay, work done by electric force to move a charge from an initial position to a final position. We write it like this. It's just equals to what we have learned from just now, equals to negative delta U. Okay, I'm not going to go through derivation. I'm going to say because last semester we have discussed this to be true, this will continue to be true for cases involving a pair of charges. Okay, and continuing from that, there's also another work done, which is the work done by external force, right? So they are exactly the same thing, work done by external force. The same work done by external force as the gravity case, as the case on the left. So I believe it is even more convincing that you can just bring over the conclusion that you have derived on the left. So on the left, we have derived that work done by external force is equal to delta U. Oops. So the same thing can be mentioned again. You can say that the work done by the external force to bring this charge over here from an initial position to a final position, so from initial position to final position, is also equals to delta U, but this time there's no negative sign. Okay, I'm just going to shift the conclusion we have obtained from the gravity case to the electric case, assuming that they behave almost very similar. Okay, once again you see that there's two types of work done. One has a negative sign, one without a negative sign, and because they differ by sign, again we can come up with this conclusion at the end, saying that the work done by the electric force is actually just a negative of the work done by the external force. Okay, very straightforward. Okay, so this is one part that I think many of us are reluctant to teach about it because it makes students confused. Why is there two types of work done? Well, okay, why is there two types of work done in this chapter is because we call this chapter electrostatics, right? So if we call this chapter as electrostatics, that means by the electric charges, the electro should be static. So if it's supposed to be static, it's supposed to be not moving, right? Okay, so if you really want to move a charge in a chapter called electrostatic, you have to move it as if it is not moving. Okay, you don't want any kinetic energy to be involved in our story here. It makes things much more complicated. Okay, you want to move the charges in the way it is static. Okay, so means by the process of moving this charge from this nearer to Q1 position to a further away from Q1 kind of position, the process of moving it here have to be done so slowly. So slowly, it is as if the whole thing never moved at all. Okay, we call this kind of situation as quasi-static or quasi-static. Means like semi-static or fixed static. Okay, something like that. It is as if it is static, but it's actually not static. We want it to move so slow that you don't even notice it. That's why I'm saying that constant velocity. Constant velocity of how much? Constant velocity of 0. Okay, it's a bit of a difficult concept to grab actually. You want to move the charge, but you don't want them to move. So you want to move so slow, it is as if that it is not moving. You want them to move as if it is not moving. So therefore, the velocity need to be kept at 0, but moving slowly from the initial position to the final position. So if you want them to move slowly at a constant velocity of 0, which is called not moving but moving, quasi-static, the constant velocity must be obey. So constant velocity must be obey means, but if you have an electric force, you cannot just leave it as electric force. You need to balance the electric force with another force. And that another force, we're going to call it as external force. And because there's two forces involved, there'll be two work done that we can calculate. And because these two forces are always balanced, their work done will be the same value, just that they are opposite in sign. So there's two work done by electric and work done by external, and they are just differing in sign. Okay, in our exam question can ask about work done by electric force. Question can also ask about work done by external force. So how do you notice whether the question is asking for work done by electric force or they're asking for work done by external force? Well, you can just read the question carefully actually. Okay, if the question mention explicitly if the question mention explicitly, let's say like work done by electric force, or the question says something like work done by electric field, or the question says something like work done by the charge. Okay, if you see keywords like this being mentioned in the situation or in the question, then you know that that work done is referring to work done by the electric force because they mentioned explicitly. Okay, however, if the question does not mention explicitly, if question does not mention does not mention any of the above. Okay, it means it doesn't mention work done by electric force, it doesn't mention work done by electric field, it doesn't mention work done by the charge. If it doesn't mention anything of here, then you can immediately assume it's work done by external force. Okay, if they want to talk about the work done by electric force, they have to be very explicit in talking about the electric force. But if they don't write it specifically, they are talking about the electric force, then you can immediately assume they are just talking about the external force. Okay, usually they will use words like, okay, for example, they will say something like work required, okay, or they say work needed, but they don't say it's done by the electric force. They don't say it's done by the electric field. They don't say it's done by the charge. They just say something like work required. Okay, if you see keywords like work required, work needed, but they didn't mention the electric force, electric field, or charge, immediately you know this is work done by external force. Okay, because it's required to keep the velocity constant at 0. Okay, if you just have this F electric only, you know that it will accelerate. That's not the case we want. So we require another force, which is the external force, to keep the force balance so that it moves at a constant velocity at 0. So this is called work required. Okay, so if you say work required, you know it's work done by external force. If you say work done by electric force, work done by electric field, or work done by electric charge, it's work done by electric force. If it doesn't mention any of the thing over here, work done by the external force. Okay, so I hope you have a rough idea of what is work done based on the concept we have learned from last semester. And I shift it, I'm going to transfer the knowledge from last semester to this semester and say that the work done by this electric force over here will be equals to this change of electric potential energy. We know the spring change its length already, so the amount of potential energy stored in this spring will have changed. So the change of the potential energy that we know over here can be related to the work done by this force over here. Okay, if you want to relate it to the external force, yes, you can. The work done by the external force will just be the change of electric potential that happens, electric potential energy that happens to this system over here as these charges Q2 move from this initial position to this final position. The change in position causes a change in potential energy. The change in potential energy will just be equal to the work done by this external force over here. Okay, so know that there are two work done over here. So I'm going to make a pause over here because I think I've conveyed what I want to convey, which I have already let you understand. I already tried to visualize to you how you can imagine about electric potential energy. Then afterwards, I relate the electric potential energy to something called work done. Okay, I relate to work done so that you have a clear idea of the relationship between work done and electric potential energy. Why do I want to relate this thing? Is because later I want to come back to this definition over here and properly unpack this definition over here. I only write for you the definition over here, but I never really explained it yet. So in the next part of the video, next part of the explanation, I'll explain this definition using the mathematics we have derived over here. Then from this equation, we're going to derive the equation for electric potential energy. So stay tuned for the next part of the explanation.